Version 12 relies exclusively on INI files to store settings. It also uses INI files to save data for exporting and importing. To avoid problems with formatting and default characters, when using different regional settings in Windows, version 12 forces all programs to use US-centric settings, as shown in the information on the screen.
Welcome to this tutorial on the Lightcurve analysis engine in version 12 of MPO Canopus. Before going on, if you haven't created the tutorials profile, you should watch the tutorial profiles video found on the MPO software YouTube channel. While not critical for the most part in this case, it will be for almost all tutorials. There are 4 programs that use the engine. With few, mostly minor exceptions, the user interface is the same in all 4 programs and, more important, each one works in the same general way to find light curves, periods, and times of minimum or maximum. With this in mind, this tutorial will use the standalone asteroid Lightcurve analysis program since it has a few more options and controls to be covered. Where and when needed, differences with variable star analysis will be mentioned. These are the general steps that will be followed. There is a lot to cover, and so several planned breaks are included, both to avoid information overload, but also to let you stop and work with what you've learned so far. When ready, you can pick up where you left off. If you're working with data generated from other tutorials that use the example images, you may not get the same results. For example, when measuring the 3 nights of images for 2002 KL6, you may have chosen different comp stars. Ideally, and usually practically, this won't matter. Do not let this get in the way of learning the steps. The goal is to learn and become comfortable with the steps, not to duplicate results exactly. As much as is possible, when working with asteroids and variable stars, analysis will become easier over time. Start the MPO launcher and open the analysis group. Now click on asteroid/TOM and wait for the program to appear. Confirm that the profile is set to tutorials and then go to the plotting tab. When there, set the normalized plot and Gantt plot switches to yes. Save the settings.
It will be faster to get familiar with the core elements of the Lightcurve engine before starting to use it. Let's start with the first part of the core options. Note that once you have generated a Lightcurve plot, changing the state of most of these controls immediately updates the Lightcurve. It is not necessary to do the period search again, since the options do not affect the search itself. Errors are the error bars at each observation. In asteroid Lightcurve analysis, the general practice is to include corrections to counter changing phase angle and the asteroid's Earth and Sun distances. This means the No HG box is not checked. On the other hand, checking the box allows you to see that the raw magnitudes are following the expected steady trend as the asteroid's average magnitude increases or decreases. Problematic sessions can be more readily seen and reviewed this way. HP amp, meaning amplitudes to 3 decimal places, should not be checked in almost all cases. It's justified only when your data truly are of millimag precision. Overstating precision in any data result is often viewed with skepticism. Changing the fixed setting updates the Lightcurve, with some exceptions. For example, if the range of the raw data exceed the fixed range, the fixed setting is ignored, unless you change the range to be larger than the peak-to-peak amplitude of the raw data. Changing the period days setting does not automatically update the Lightcurve. This is a case where the period search must be run again. Auto-period search does not immediately affect the current Lightcurve. It does, however, affect what happens as you edit the data points in a Lightcurve. Yes means that any change prompts a new period search. If you have a number of points to exclude, this could get very tedious. No is the better option here. There is much more on editing data yet to come. The tiny button in the bottom row resets the size of the form, but only as little as possible to make the plot area have the same aspect ratio as the plot settings shown in the lower left. It's not required that you use it, but doing so allows you to confirm that the final plot doesn't have unexpected results, such as the legend overlapping into the plot area, or the title being too wide. Selecting Profile in the Plots drop-down list uses the settings on the Configuration Plotting tab. Otherwise, you can override the default using one of several preset options, all with a 4:3 aspect ratio, or even custom settings. Carefully determined and applied transforms applied on the fly can further improve the quality of the computed data by reducing errors due to color differences among the comps and target. Remember that MPO Canopus always stores raw, uncorrected data. Including transforms modifies only the data loaded into the analysis engine. The standalone asteroid and variable star analysis programs allows working with other than the standard photometry SDB files. This allows you to work with data from other version 12 users, or version 10 if they send you their V10 to V12 exports files to convert. Use the Sessions Manager program if you want to merge multiple database files into a common file. In this case, we are using the standard photometry SDB file, which has 3 sessions that were created during the tutorial on multi-image asteroid photometry. Set the Select drop-down list to limit the sessions to those that use the filter. Choose any to find all sessions with a given name. Click the Object button. This displays the Select Sessions form, which is a redesigned user interface of the version 10 form. There are 3 ways to search for sessions. The ID is the same as the ARB session number in version 10. It will probably be the least used sort order for searching. Name is the full session name. Date is the mid-UT date time of the observations in the session. You can choose among 3 places where the search starts. Top always starts with the first record in the current sorting order and scans down until it finds the first matching record. This is good to find the first session of several, but using it to continue the search will never get past that first record. Down starts with the current record and searches towards the last record. If there are multiple sessions after the first one found, choosing this direction will find the next immediate matching record. Up works the same as down, except it moves towards the first record in search order. Neither the up or down search wraps around. They always stop when they reach, respectively, the top or bottom of the table. This can give a false impression that there are no matching records. For example, if you choose down, then even though there might be 20 matching records, if they are all before the current record, they will not be found. Wildcard characters in SQL databases are the %, not the common asterisk used in Windows Explorer. A search on ID must match exactly, it does not on a wildcards. As shown in the examples, it's possible to be creative with wildcards when searching by name. Dates can be limited to a year or year-month combination when using wildcards, or limited to a specific year-month date. Beyond that, a search for dates using wildcards is unpredictable. For example, you cannot search for all the sessions made on the 7th of an unknown month for a single or unknown year. Once you have found the first session you want to analyze, you have 2 options. First, click on any of the matching sessions and then click the OK button. This selects all matching records. Or, you can click on a matching session and then check the filter checkbox. This limits the records shown in the table to those matching the session name, and filter if other than any. Once the table is limited to the matching sessions, you can select a subset of records. If you want to select all of them, uncheck the box and click on any one of the matching records. Shift+click does not work to select a contiguous set of records. So, click on the first record in the subset, and then Ctrl+click on any other record that you want to include. The most recently selected record has a double right arrow in the far left column. All other selected records have a dark dot. As you change the subset, the selected count is shown at bottom right. Click the OK button when done selecting sessions. The selected sessions are transferred to the top list on the Options panel. Click the Roll-up button if some of the selected sessions are not seen. This hides some of the controls at the top of the Options panel to make more room for the two lists. Use the button again to see all the controls again. The splitter bar between the two lists is used to change the relative heights of the two lists. The Select Sessions form, letter A, shows all the sessions that you might want to analyze, those that matched your search parameters. Letter B is the set of sessions that you selected in the Sessions form to be involved in analysis. Letter C is the set of sessions to be used in the period search. For example, you may have sessions from 3 different apparitions, but want to analyze data from just 2 of them. You would select the sessions from those 2 apparitions in A, which moves them to list B. In most cases, you won't mix data from different apparitions, and sometimes use a subset of an apparition if the light curve changed dramatically over the span of the observations. So, you select only those sessions from a given apparition, or a subset of one, to move into list C. These are the ones that can be used for analysis. In the top list, B, there is a difference between clicking on the checkbox in a line and on the name. When a box is checked, its session is immediately copied to the bottom, or C list. There is a delay while this happens. It can be tedious if there are many sessions involved. To move multiple sessions to the C list, click on the names not boxes in the list for all of the sessions to create a set of selected records, and click the red check mark under the B list to copy them to the C list. This is much faster. Click the prohibited button under the B list to clear all the checks. Unchecking a box in the top or B list is like a product recall. Those recalled sessions are removed from the bottom C list. We've switched back to the tutorial database, which contains data obtained by measuring the set of example images for 3 nights on 154, 244, 2002 KL6. In the C list, click the check of a session to make it part of the analysis. Check the red check button under the C list to set the check for all sessions. Click the prohibited button under the C list to clear all the checks. As you'll see, you can have several sessions in the C list, but choose to plot the data for only one or some of the sessions. X marks the spot. It's time to take a break. I'll take a tall black, please. If you haven't already, you should measure all 3 nights of example images for 2002 KL6 before going to the next session. The tutorial on multi-image asteroid photometry works with those images. If you have some sessions in your photometry database, then before you start again, spend some time working with what you've seen so that you can get comfortable with searching for sessions, selecting 1 or more sessions to be part of the analysis pool, and then selecting which sessions will be used for a given analysis run.
Welcome back. If you haven't measured all 3 nights of the example images of 154, 244, 2002 KL6, you should do that before going on. If you have, then using the skills learned so far, select all 3 sessions into the B and C lists. Click on the Comps tab. The Comps tab has 4 main sections. The drop-down list at the top has all the selected sessions from the C list. The drop-down list below that shows which comp star in the session is being viewed in the top plot. If you change the state of one of the boxes in the C list, this resets the drop-down lists and triggers a flurry of updates. The Data Radio button determines how the data are calculated. If set to raw, the plots are sky magnitudes versus JD in both plots. If set to average, the values in the top plot are the selected comp magnitude minus the average magnitude of all the other used comp stars. The bottom plot shows the target minus comp magnitude for each comp versus the average of all the target minus comp magnitudes. The standard deviation value in the bottom plot header changes as you change the comp star in the second drop-down list. The standard deviation of the mean of those individual standard deviations sets the error bars level. Ideally, the bottom plot should have all lines on top of one another, and errors would be 0. The goal is to find the largest number of comps that produce a spread of the individual lines in the bottom plot, with as small a spread as possible. Set the auto update switch to yes for now. This controls when the program recalculates the derived magnitudes. If the auto period search switch is set to yes, then a new period search is executed. When set to yes, changing the state of a checkbox in the comps list immediately triggers those actions. This takes time. Trying to make several changes too quickly will likely cause the program to complain bitterly. Note that in the comps list, clicking the box or the name is the same thing. If you want to modify more than just one or two comps, set auto update to no. The requests are put into a queue, and the auto period switch setting is ignored. You must click the update button below the comps list to process those requests. If you don't update before doing a new period search manually, the requests are lost, and the period search uses the pre-edited state. Use these next two buttons only if the auto update switch is set to no. Click the green check button under the comps list to set the check for all selected comps. Remember, there is a difference between being checked and being selected. Click the red X button to clear the checks for all comps. The only reason to use the C list at this point is to include or exclude a session from the calculations. Either action resets all the other items on the tab. To select from the sessions to review, use the top drop-down list. Set auto period search to no. This is generally a good idea until you've done all, or most, of comp star editing. Otherwise, every change to a comp recomputes the period. Select session 1 and C1. Set data to average. Set scaling to 1.0 mag. This sets the Y-scale range on both plots. Use expand to have the bottom plot scale to about 1/2 the full range of magnitudes. Set auto update to no in order to avoid updating problems during the next step. Make sure all comps are checked. Reset auto update to yes. Remember, it's the process, not the actual numbers, that matter. When measuring the images for the asteroid, you may have chosen a different set of comp stars, and so what you see in the video may not match your computer screen. Click on a data point that appears to be a bad comp star. In this case, the bottom status bar reports that the point is in session 1. Control+click on the data point, and confirm the message to remove the entire observation from the calculations. If a comp star has one bad observation, but all the others in that observation are okay, you don't have to delete the entire observation. Control+click on the data point in the top plot, which should be showing the comp in question. Confirm the request to exclude the comp for the one observation. Note that the two plots mirror one another. If a point is high on the top plot, it is low on the bottom plot. However, this may create a circular problem. Either right after excluding the data point, or maybe later on, as you edit other comps, you'll find another comp star for the same observation needs editing. Eventually, it's just easier to delete the entire observation. Some target minus comp lines are significantly above or below the others. In this case, comp 7 in session 3 is one of those outliers. If you don't want to have the program recalculate all the data points on the two plots, set auto update to no. If set to yes, it can take a few seconds for the program to recalculate all the target minus comp values. Uncheck comp 7 in the comps list to drop it from the calculations. It appears that comp 2 in session 3 is also an outlier. Remove it from the calculations the same way as you did comp 7. Repeat the review until you're satisfied with the comp set. Don't get too aggressive and whittle your way to one comp star. Keep as many as possible. Here are the results after editing session 3. We switched the scaling to expanded to get the best possible look. This makes the scatter look larger than it is, and you may be tempted to remove more comps than necessary. In this case, the spread is actually only plus or minus 0.03 mag. Here are the results after editing all 3 sessions. Again, your results may not be the same. Before trying an actual period search, plot each session's raw light curve one at a time. Editing the comps reduced the error bars, but it did not necessarily remove any or all bad observations. From a raw plot that appears to cover a full or half cycle, you can set the initial period search parameters. To make things go faster, especially with a large number of data points, set the steps to 1. This means one and only one period is examined. It may be entirely wrong, but that gets fixed in the next chapter. Here are the raw plots for the 3 sessions, immediately after editing the comps. The error bars are low for the first 2, and a little higher for the third. Only the second Lightcurve appears to have some bad data points. Set the auto period search switch to yes if there are only a couple of obviously bad data points. Set the switch to no if you appear to have a larger number of supposedly bad data points. Be careful about how you define a bad data point. As you'll see later, you may exclude evidence of the asteroid being binary. Ctrl+click on a data point to be excluded, and confirm the request. With auto period search set to yes, you'll see the immediate effect. This brings up an important point. Sometimes eliminating just one data point can alter the period solution dramatically. Be open to not having the correct period search parameters. Otherwise, you may delete data points that are perfectly valid when plotting the data to the true period. What if there are more than a few obviously bad data points? For example, if clouds move through the field. Deleting them one at a time would be too time-consuming. Place the mouse cursor above and to the left of the first data point. Drag the mouse down and to the right to outline the region of points to exclude. Make sure that only the data points to be excluded are showing before the next step, which is Shift Control Function key 12, to exclude the data points. Since auto period search was set to yes, the program zooms the plot back to 100% and replots the raw data. The offending data points are gone. If auto period search was set to no, the data points are flagged to be excluded, but they are still visible. Unzoom to 100% and click the search button to update the plot. You deleted all the data points in the session. This can and has happened if you are too quick to press the keystrokes to exclude. If it does happen, go to the Observations tab and check all the observations for the affected session. You'll lose any work regarding bad data points in the raw plot, but this does not automatically reset the comp stars. That is a separate operation. Click on the Observations tab. The target and check star, if you are using the variable star analysis program, are shown in the top list. The comp observations for the highlighted target observation are shown in the bottom list. Both lists are multi-select, which allows updating the check status of several records in one step. It's important to keep in mind that there is a difference between checking a box on a line and clicking elsewhere on the line. When working on this tab, it's recommended that you set auto period search to no. Each time you click on a checkbox in either list, the program recomputes all the data for the chosen session. Depending on the number of data points in the session, this can take several seconds. If you're going to do more than one observation, you'll spend a lot of time waiting for the program.
It's time for another break. Take some time to get comfortable with everything so far. This will be assumed in the analysis sections to come so that you can concentrate on new information. This will not and cannot be a thorough explanation of Lightcurve analysis. You'll learn the controls involved, the mechanics of how to generate Lightcurve, and some general tips for finding the correct period. The resources listed here will go a long way to help with your analysis work. MPO Canopus always stores the raw observations. It is only during analysis that the necessary adjustments are applied to achieve the net effect of having all observations made at exactly the same time using the same comp stars. Any periodic variations, not due to systematic errors, would presumably be due to an asteroid's rotation or a variable star changing brightness. It's good to have a rough idea of the period for one cycle. This can be taken from the literature, without too much precision, or reviewing a raw plot of a single session that appears to cover at least half a cycle. The data from 3 nights for asteroid 2002 KL6 will be used here. To plot a single session, set the controls in the list to the values shown here. Fourier curve display is off, because the curve can take very wild gyrations until they are enough to avoid large gaps in coverage. Since an asteroid is being analyzed, be sure to uncheck the period days box. The type of light time correction is set in the configuration of the profile. It is either based on Earth asteroid distance or a correction to heliocentric JD. It cannot be changed here. The symbol sizes are suggested. Change them to suit your preferences, though keep in mind that adjusting the size based on the height and width of the chart may be something to consider. Larger plots would use larger symbols. The correct number of harmonic orders depends on the amount of data and the complexity of the light curve. Start low and go higher as you refine the solution. For asteroids, 4 is a good starting point. For one type of Lyrae stars that have a very sharp rise to maximum, then 8 might be a good choice, but only if the data cover the rise and the complete maximum. Before clicking the search button, make sure that all the sessions you want to use are checked in the C list, the one at the bottom right. This was a very easy target. PR stands for pan-stars, are magnitudes that were taken from the Atlas catalogue. This made it possible to have no nightly 0-point adjustments, although some fine tweaking might have improved the result a little. The Fourier curve in the initial solution didn't quite follow the data. Using a higher order for the search helped fix this, as did refining the period search to a smaller range centered on the initial period. Avoid the temptation to get results that are more precise than the data allow. Adjusting the nightly 0 points is easy, but it can also hinder finding the right solution. Long period and tumbling asteroids have been overlooked because of overzealous adjustments. Click on the session in the C list that is to be adjusted and then click on the fixed entry field, where you should start at 0.0 if this is the first time the session has been analyzed. Enter a new value or use the spinner control to change the offset value, or delta comp, as it was called in version 10. Changing the delta comp value does not automatically update the session data, nor necessarily cause a new period search. Click the Recycle button to have the change take effect and be saved permanently to the session's record. The setting of the Auto Period Search switch sets when the updates are seen on the plot and affect the period search. If set to Yes, then clicking the Recycle button immediately applies the update and runs the period search again. If set to No, the updates are not seen in the plot or affect the period until you click the search button again.
This method to find a best fit of all sessions at one time applies to asteroids only. This is done by changing the value of the phase slope parameter, g, in the HG system, to adjust the corrections applied to the sessions to put them on the same 0 point. The steps to do this are outlined on the screen, and would be done when selecting the sessions for the object to be available for analysis. This works only if the data span a wide enough range of phase angles. 3 consecutive nights on a main belt asteroid would show no difference in the fit between using the default 0.15 and a different value. It should also be used only when the data values have been put on a common 0 point, in other words, have had photometric reductions applied. Make sure the new value of G fits the taxonomic class of the asteroid. It won't do to use a value of 0.05, normally for a dark type C, when the asteroid is actually a type E, where the average value is about 0.4. Using the wrong value of G when updating the absolute magnitude, H, can lead to a very wrong value, which in turn gives a bad diameter for the asteroid. What can you do when you can't make a first good guess for the period of the object? Here, you use a different set of parameters, the first being to set the search type to period auto. This generates a geometric series of trial periods that are used to find a minimum RMS fit. The auto search settings for the minimum, size, and steps are a bit confusing. Minimum is still the shortest period, but the size value tied with the number of steps determines the actual number of steps and the maximum period. In these settings, the search starts at 1 hour and goes up to about 25 hours. Be careful with the parameters. For example, if using a minimum of 1, step size of 1, and steps of 400, the number of trial periods is enormous. you'll have a very long wait for the program to finish. The initial results are close, but the precision is far too high given the data set. The period spectrum shows hundreds of data points, even though the search parameters might make you think otherwise. To get a final result, return to the LC1 tab and redo the search, setting the type to period regular and centering the period range on the initial solution, making sure that you cover a large enough range of periods. In this case, start with 4.5, 0.001, and 300 steps. This will cover 4.50 to 4.80 hours. Click on PS1 to see the period spectrum for the period 1 search. This plot shows the RMS value of the fit versus the trial period. Usually, the x-axis uses a logarithmic scale, but you can switch to linear, which is shown in the bottom plot. Click on a data point to see its information. You cannot delete data points. On its own, the period spectrum shows a large number of reasonable possibilities, especially for the half period at about 2.3 hours. The relatively low solar phase angle and amplitude of 0.76 magnitudes strongly favors the bimodal solution near 4.6 hours. Click the plot button to save the period spectrum to a PNG bitmap in a directory of your choosing. The initial default is the plot subdirectory under the MPO V12 root. Click the Data button to save the Fourier data. These are used on the LC Gen tab to produce past and future light curves. The data are automatically saved in the UData subdirectory of the MPO V12 root. Click the View button to see the Fourier data in a read-only text viewer, where you can save the contents to a directory of your choosing. It is the same format as that generated by the Data button. There is a separate period spectrum tab for each Lightcurve tab. The list box shows some of the output of the FALC program by Alan Harris. The U1 and U2 values are used internally to find the best RMS fit. They are not needed anywhere else in MPO Canopus. It looks like the auto search method found a reasonable first solution. Return to the LC1 tab, reset the search parameters to use period reg, and a combination of a minimum period, step size, and steps that is centered on the most likely period. The number of orders in the search depends on many things, but, generally, on the amplitude and complexity of the light curve. Light curves with large amplitudes or, in the case of some variable stars, that have a meteoric ride from one extremum to the next, will need higher orders so that the Fourier curve follows the data as closely as possible. A total of 4 solutions with a fixed period of 4.614 hours for 2002 KL6 were plotted, the only difference being the number of orders. The table of RMS and amplitude versus the order shows that there can be a point where going to higher orders not only doesn't improve the solution, but makes it worse based on the RMS value. Look at the highlighted regions of the 8th and 15th order plots. In the latter, the curve tries to make a compromise between the general average trend and some data points that deviate from the average. More is not always better. To find the optimum number of orders, set the search parameters as shown on the screen. It's important that you use a good period found with a previous search effort. The value in the ORD field is ignored. The step size is still used to compute the formal error of the period. Steps is the maximum number of orders that you want to consider. The search always starts with an order of 1 and can go up to the maximum of 15. In this case, the search will cover all the allowed possibilities. Once you run the search, go to the PS1 tab and look at the bottom right. Ignore the plot itself, since all the X values are exactly the same. The highlighted line shows the order that gave the lowest RMS value. In most cases, the next highest even-numbered order is adopted, but only if the actual and adopted value don't change the final light curve results. This might occur when the data set is relatively sparse, especially if the light curve has a smaller amplitude, and/or the shape is not close to being symmetrically bimodal.
This will be an overview of how to find the 2 periods in a binary asteroid that shows mutual events. The feature can be used for any object, including variable stars, that appear to have at least 2 periods. One thing MPO Canopus cannot do, however, is resolve the periods of rotation and precession of a tumbling asteroid. You won't be measuring any images in this part of the tutorial. Instead, you will load and export a database that includes the photometry of a binary asteroid. The same basic steps would be used to load any V12 photometry database for analysis. Click the red-blue dual computer button just to the right of the Object button. A small pop-up menu appears. One item is Photometry, which reloads the photometry SDB file in the MPO v12 databases directory. Click on the second option, Import, to display a file open dialog and navigate to the location under the MPO v12 examples directory shown here. Select the SDB file and then click the Open button on the dialog. The full path of the import database is shown at the lower left, and the B and C lists are filled with all available sessions. You won't need to review the data on the Comps tab. That was done before creating the file, but it won't hurt to do so, and you will know more about the data you are using. The dual period process is iterative. You find a presumed dominant period and remove it from the calculations to do a search for a second period. If you find one, you go back and subtract period 2 to find a better solution for period 1, which is used to find a refined period 2, and so on. This continues until the two periods stabilize. Use the search parameters shown on the screen to run an initial search. A narrower range of trial periods was made possible by looking at the raw data. This will not always be the case. The initial search seems to have found a good solution, as shown by the Lightcurve and period spectrum. Don't be too quick to exclude supposedly bad data points. In this case, there is gold in that noise. In general, except for very obvious outliers, keep all data until you're sure you're on the right track to find a single or dual period solution. This is where experience and a general idea of the range of likely secondary periods for a binary are helpful. The parameters on the screen perform a search from 5 to 35 hours in steps of 0.02 hours. Alternately, you could use the auto search starting with the same minimum, a step size of 1, and a number of steps of between 30 and 50. This may be faster for large data sets. The search found what appears to be a solution that produces a dip that might be caused by mutual events, which are occultations and eclipses involving the satellite. However, it's a good idea to look for a Lightcurve with two attenuations that are closer to 1/2 the period apart. Let's do a search that gets out to at least double the current best solution. Using the search parameters on the screen, a more likely solution was found at about 51 hours. Your search may lock onto the almost as likely period of about 45 hours. This one is not going to be easy. To be safe, take Stay on the L2 tab and look at that second possibility, which was about 45 hours in this case. Using search parameters that covered a range of 44 to 46 hours, a good solution was found at 45.07 hours. Which is the right one? If using the period spectrum, the longer solution seems better, but this could be a case of what's called a fit by exclusion. This comes about when the Fourier analysis finds a false minimum, IMS, by reducing the number of overlapping data points. A longer period will mean fewer data points will be from the second cycle. It's a form of excluding bad data by making them fit a different period. We'll use the 45-hour solution to refine period 1, so let's return to the LC1 tab. Finds a false minimum, IMS, by reducing the number of overlapping data points. Use the search parameters on the screen to search over a narrower range of trial periods, now using a precision of 0.001 mag. This produces a very nice bimodal Lightcurve with almost all the noise from the first try removed. The period spectrum shows the solution, at least in the range it covers, is not ambiguous in any way. So far, there have been no zero-point adjustments. Avoid those if at all possible until there is sufficient confidence in the two periods. Otherwise, a slight adjustment in one or more sessions can lead you down a dark path. Trust the data until you can't. Back to the LC2 tab. On the presumption that a period near 45 hours is actually better, use the search parameters shown on the screen to scan a range of 40 to 60 hours in 0.1 hour steps. This allows covering both of the contending periods. The shorter period is now favored, even if only by a little. The one concern is that the events are not exactly 1/2 cycle apart, whereas they are with the longer period. When in doubt, check it out. This means staying on the LC2 tab and running a narrower search near 50 hours. The events are more evenly spaced, but the fit to the data is not as good. Session 4 at about 0.37 phase doesn't fit the curve at all. Don't fall into a trap of dropping a session or two just because they are out of step. While not the case here, the misfit could be because the asteroid is tumbling or there is some other physical cause. Don't commit the worst kind of fit by exclusion, ignoring valid data. To refine the periods a little more and gain greater confidence in the longer solution, do one more cycle of period 1 period 2 searches, each time narrowing the search range some, but staying centered on the current best period. These are the final results. Both light curves have good fits to their Fourier curve and almost all the noise is gone. Note that the P2 plot has a vertical range of about 0.16 mag. Some might want to let the curve fill the screen using a smaller range on the y-axis, but this emphasizes the noise too much and can trick you into incorrectly excluding data points, or thinking you don't have the right solution. Sometimes it's best to step back and take a wider view. Other than being binary and having an orbital period of about 45 hours, what more can be learned? For one, the ratio of the effective diameters of the satellite and primary. Use the depth of the shallower event in the formula to compute the ratio. This gives something close to 0.34. What else? For one, because the events are not flat-bottomed, the events are partial, not total, and so the ratio of 0.34 is a minimum. Another is that the shape of the light curve outside the events is nearly flat, which indicates that the satellite is only slightly elliptical, and, because there is no third period that might say otherwise, the rotation period of the satellite is tidally locked to the orbital period. That's quite a bit to know from just measuring the variations in the asteroid's brightness over a short period of time. This is a good time to take a final break, so that you can work with the tutorial data, or your own to find light curves and periods. There are additional plots and features on the Lightcurve engine worth knowing, but you can come back to those after the break or even a later date. Whichever you choose, it is worth the short time it will take to view the last sections so that you can get the most out of the programs.
There are two options on the configuration plotting page that allow seeing two additional plots, a Gantt chart and a normalized light curve. Check out your profile settings and, if necessary, move both of the two switches from hide to show. Whenever you do a period search, the program can create a Gantt chart, which shows the location of each session in the group of all sessions. If you're working alone from a single location, you mostly see if the sessions varied in length, and if there were gaps between sessions due to clouds or other factors. This plot is most useful when compiling sessions from multiple observers, located at different longitudes. In this case, with this and the light curve plot, you can see which observer contributed to which parts of the light curve. Use the switch at the bottom to hide or display the labels that appear over each session. When using a binary star modeling program, such as Binary Maker 3, the data must be converted from magnitudes to flux values, and then normalized to values between 0 and 1.0. The largest flux value, actually the average of several on either side, is set to 1. All others have lower values. The two sets of entry fields, and scroll bars next to them, allow you to tweak the data in phase and normalization. Use the Graph button to save the data in a format compatible with Binary Maker 3. The Plot button saves the normalized plot to a directory of your choosing. The LC generator is a great planning tool. Say you want to see when one of the events of a binary asteroid, or the next maximum of a variable star, occurs when it's dark at your location. This tool does the job. The first step is to load the Fourier data saved after finding the rotation period of an asteroid, the orbital period of a satellite, or the period of a variable star. First, enter the starting UT date and time in their fields. Click the Load Data button to display a File Open dialog. Locate the Fourier data file, and click the Open button on the dialog. The program automatically fills the remaining fields using the data from the file, and generates a curve for about 2 full cycles after the start date and time. Beware that even when working with an asteroid, the period and length of the ephemeris are in days. At first, you should not change any of the values, except the date, time, and days fields, the latter being how many days the ephemeris will compute beyond the start date and time. Later, if you want to see the effect of a very small change in the period over a long range of time, change the value, in days, in the period field. A number with a total of 10 digits, and the decimal point can be entered. The 7 decimal place value seen here has a precision of about 0.01 seconds. Click the LTC button to compute the Earth asteroid or heliocentric JD correction to the data. For an asteroid, a lookup table for the MPC orb file is shown. For a variable star, a small form appears, where you enter the RA and declination of the star. When you close either form, the program computes the correction and displays it in the LTC label. MPO Canopus stored the midday time and exposure from the FITS header. Presumably, the computer clock is running on Earth-based local or UT time. For proper light curve analysis, the data must be corrected. For an asteroid, the correction is to the time light left the asteroid, not when it reached Earth. For a variable star, the fixed location of the Sun's center, the heliocentric center, is used. However, the Sun orbits about the gravitational center, or the barycenter, of the Solar System. Even though that point is well inside the Sun, the difference can be significant when the highest of precision and accuracy are needed. Check the Use LTC box to include the correction. The change is reflected immediately in the ephemeris curve. It is not necessary to regenerate the ephemeris. Check the X-axis UT box.
Finding an accurate time of minimum or maximum, TOM for short, is of great importance in variable star work. Over months or years, even a very small error in the period can accumulate such that making an accurate prediction of a future event is uncertain at best. Computing the difference between the observed and computed time of the event can show, among other things, if the original period was incorrect, the original 0-point epoch was incorrect, and most important, if the differences follow a trend that indicates that the period is changing in a linear or more complex way. You cannot find the time of minimum for more than one session at a time, and you must use the raw data, not those from a period-phased light curve. Otherwise, you're getting a TOM that based on any number of TOM values that may or may not be based on an extremely accurate period. The variable XX Andromeda is not from the tutorial images, but a much larger database of variable star sessions. It is not included with the tutorials, so you need to concentrate on learning the process. Then you can apply what you've learned to the tutorial data, or some of your own. XX Andromeda is a subtype of the RR Lyrae class that has an extremely fast rise from minimum to maximum, and then spends the great majority of the cycle descending to the next minimum. The type of TOM depends on the type of variable star, the notable example being eclipsing binaries where the time of minimum is found. The first step is to use all valid sessions to find as accurate of a period as possible. Once you do, Control-Shift-click on the min field and answer yes. This transfers the derived period, not the value in the min field, to the TOM page. If you're working an asteroid with periods in hours, note that the period is changed to days in the min field. Keep this in mind should you try another period search. In the C list, which has the sessions that were used for analysis, check only session 536. Click the search button on the LC1 tab to update the internal data lists. Click on the TOM tab. Click the M-R radio button. This indicates that the search is based on the time of maximum, using the raw data, and not the Fourier curve maximum. The two are very often not at the same time, especially if there is a rogue data point or two at the maximum. Click the button in the mid-JD field to transfer the JD of the extremum value corresponding to the chosen search type. In this case, the JD of the maximum raw data point for session 536. For now, leave steps at 11 and the size at 0.0001 days. These values are dependent on the number of data points on either side of the extremum and time interval between them. Click the PS1 button to say that you're working with the results of the period 1 search. Or click the PS2 button if you're trying to find the TOM of the second period. Click the stopwatch button to show the results as a JD in the entry field, and as a calendar UT date and time next to it. Let's generate the times of maximum for the 10 days before and after the computed TOM. This is why finding an accurate period beforehand was necessary. Set the controls as shown on the screen. Check Use Computed Date for the base JD of the calculations. Uncheck the box if you want to use a different base date. The Near Entry field is disabled if this box is not checked. Selecting Ephemeris generates dates and times for the computed times of maximum. Selecting phase generates the time and dates for period phases 0.1 through 0.9 in 0.1 intervals for the 10 days after the computed TOM. You can force the start date of the results by using the pop-up calendar in the Near field. You can also enter the date manually in year-month date order with or without the dash separator. For a binary asteroid, you can use the phase computations to know when to expect the upcoming mutual events. For a variable star, you can check if the computed TOM is close to the one observed 1 month, or even years later.
On rare occasions, you may want to review the individual observations in table format. Note that for variable stars, each line also includes the observation for the check star. One of those times is when you accidentally exclude all the data points in a session by being too quick to click Ctrl-Shift-F12 on one of the Lightcurve tabs. Another is when you might have excluded some data points that didn't appear to fit, but, after finding a secondary period, you want to see if you removed some evidence of that second period. Use the checkbox on each line in the observations table at top to toggle the status of the entire observation. An X indicates the observation is included in calculations, presuming that its owner session is also included. To toggle the status of several observations, use the standard Windows method to select multiple lines in a list box, clicking on the line, not the box. Each action generates its own event. After making changes, be sure to recompute any period that would involve those changes. Many of the subtle differences when using the analysis engine for asteroids or variable stars have been covered. One particular difference to note is that on the variable star analysis forms, there are not just the plots for a selected comp star and a selected session, but of the check star for that session. This plot does not allow excluding a check observation for the session, since this would render the entire observation unusable. The bottom plot must be used to exclude observations. There are also important differences in the way the dates of observations are corrected. For asteroids, the asteroid Earth light time is used while a correction to heliocentric JD is used for variable stars. Asteroid observations can be made over a wide range of viewing aspects. To find an accurate period, the effects of phase angle, changing distances of the asteroid from the Earth and Sun, and different comp stars must be taken into account. This list gives you an idea of the more frequently encountered obstacles when finding an accurate period. A rotational alias occurs when the true number of cycles over an interval cannot be established with certainty. Say you have an asteroid Lightcurve with 0.1 mag amplitude from one night that covers an extreme, but not even half of a cycle, and another from 5 days later, covering the same part and amount of the Lightcurve. Your analysis finds a period of 4.8 hours, or 25 rotations. Is that necessarily the right answer? After all, a period of 5.0 hours could easily show the exact same result, but the number of rotations would be 24, not 25. Periods that have an integral or half-integral multiple close to an integral number of Earth days can be very hard to determine.
Here are some handy hints that apply to almost all plots in the programs. Zooming in on part of a light curve can show some interesting details, such as in this case, where one session has data points that are above all others in the area. Are they real or just lesser quality data? That's for you to decide. As shown earlier, zooming in on a region of data points allows you to exclude all points in the zoom region from the calculations. To get back to 100%, drag the mouse up and left starting anywhere within the axis borders. In some cases, a plot has historical zoom enabled. This means that if you zoom in on a region and zoom in on the new region, then unzooming once gets you back to the previous zoom level. Continue until you're back to 100%. To show or hide the grid for the plot, click on the left axis line to show the horizontal lines and the bottom axis line to show the vertical lines. If showing, the grid is saved with the plot. If you hover over a data point on a plot, a fuzzy orange outline appears for that data point. If the point is in a series being shown in the legend, then the text for that series in the legend changes to red. Clicking on a data point in most plots will display information about the data point in a status bar below the plot. The information displayed depends on the plot. More tutorials can be found on the MPO YouTube channel by visiting the URL on the screen. Please subscribe so that you can be notified when new tutorials are available. If you have any questions or comments, please send them to the MPO Software Forum on IO Groups. Please note, you cannot attach files to messages. If necessary, you will be asked to send them offline. Thanks for watching.